Welcome back, Math 20-2. Today we are doing the last lesson of trigonometry. We're going to be looking at sine law, cosine law, when to use them, and also SOHCAHTOA, when that comes into play as well. We're also going to look at things from way back in grade 9. So some things you might have forgot, such as your circle geometry in grade 9. Starting off, we're going to look at SOHCAHTOA. Well, when do we use SOHCAHTOA? We use SOHCAHTOA every time it is a right triangle. This is also, whenever it's a right triangle, is also when we use the Pythagorean theorem. Now we look at the other part here. If it's a non-right angle triangle, then we have to either use sine law or cosine law. So we use cosine law if we know all three sides or if it's side angle side. An example would be if we have a triangle like this, and we know this side, and we know this angle, we know this angle, we know this side, and we know this side. That would be an example, because it's side, angle, side, where the angle is caught in between both sides. So there is an example of cosine law. Now, if I move my angle over here, this would all of a sudden be sine law. This is sine law because the angle is not in between both sides. Also, if we move the angle there, that is also going to be sine law instead. The only time the cosine law works is if the angle is right here. Okay? Everything else is sine law. So if we know all three sides are side, angle, side, where the angle's in between the two sides, then we know we have to use cosine law. All right, here we go. Now, the first part here is just going over some definitions and laws of what we learned in grade 9. So perpendicular from a circle to a chord makes the chord, does what to the chord? Well, we look at this right here. We have a circle from the center of the, we have a line from the center of a circle, and it's perpendicular to the chord. Now, what does that do? That is going to make it perpendicular, and it will bisect the chord. It will always bisect the chord. So the measure of the central angle is equal to, so now we're going to look at this one here. The second one, I'm going to use a little highlighter. So my central angle is going to be in orange, and we want to look at an inscribed angle. So an inscribed angle is one that's completely on the edges of the circle. It's made up of two chords. So I do have two inscribed angles. I have one here, and I have one here. I'm going to look at the first one that I highlighted at the beginning. So I'm going to look at the first one I highlighted at the beginning, which is this pink one here with angle y. Now, angle y and angle x, x is always bigger than y. It's the central angle, and if we notice, they're both coming from the same feet of the circle. So this one here is going to be always double angle y. Or angle y is always half of the central angle. So if they come from the same feet, it is going to be half of the central angle, or the central angle is double that one. So the central angle is double, or twice, the measure of the inscribed angle. Okay? And the inscribed angle, we said, we highlighted in pink. Now the next one says, inscribed angles subtended by the same arc. Well, we have two inscribed angles, and they're subtended by the same arc. If we look at it here, both are using C and A as their feet. Well, if this is half of x, and this one must be half of x as well, therefore y and z are the same, so they are equal. Last one says, a tangent to the circle is to the radius. So we have a tangent connected to a radius. This is always going to be perpendicular. There we go. So now we got some of those definitions out of the way. Now we're going to start on our very first problem for today. So in the diagram, O is the center, and we have the radius is 3.25, and we have two radiuses, here and here. There's one radius, there's the other, and these are both 3.25, and this one is as well 3.25. And we have PQ is 2.5, or QR is 2.5, and we have RS is 4.7. All right? Now it says calculate to the nearest whole number the length of p cubed. So we're first going to try and figure out what is that length there, p cubed. Well, I look at this angle here that goes through it. This is actually a central angle, a straight line. That is going to be 180. So the central angle, POR, is equal to 180. Now, if you remember, PQR is the inscribed angle. So, and they have the same feet, or the legs are the same. They are at the same part of the circle. It's by the same arc. So this is going to be, so we know PQR is equal to half of that. So this here has to be half, which is 90 degrees. Now we know we're dealing with a right angle triangle. That makes things so much easier. Since it's right angle triangle, we could go back and we could do things like the Pythagorean theorem. We could even do SOHCAHTOA, a lot of simple calculations. Now what do we know here? We know this side here is 3.6 because it's two radiuses. So PR is equal to 6.5. 2 raised 3.25 and 3.25 is 6.5. And we know QR is equal to 2.5. We are trying to find PQ, and PQ is not the hypotenuse, it's just an average side. So what we're going to do is we use our Pythagorean theorem. The hypotenuse we know, so we end up switching it, so c squared minus b squared is equal to a squared. A squared is going to be PQ. PQ squared is equal to, well, my radius is 6.5, and we're minusing 2.5 squared. After I do all of this, I'm going to get PQ is equal to 36. So then that's PQ squared is equal to 36, so then PQ is going to be only equal to 6. So calculate. Okay? Next one. We want the measure of QPR. So the measure of angle QPR. So that is this angle right here. Well, if I look at this, I know this distance here and this distance here. I know my hypotenuse is 6.5. We also know my opposite is 2.5. So now, the opposite of that angle is 2.5. So now we could just use which trig ratio works? Sine. So SOHCAHTOA. Sine, and I'm going to say P, because it's angle P, is equal to, we have opposite, 2.5, divided by 6.5. So then the angle is equal to the inverse of sine. All right, and we plug that into our calculator, and I am going to end up getting a total of 23 degrees is equal to angle P. Okay? Now the last one, it wants the measure of SQR. All right, so we look back to our circle. We want SQR. So let's highlight that. I'm going to highlight this here right now in pink. So we want SQR, like that. Now, we have to look at what else is there that we know. If I take a look at this, that's the one we know, but I could find, I believe, this angle here. How? If I look at those, aren't those the same? These are both inscribed angles with the same feet, so they're subtended by the same arc. Therefore, angle P is equal to angle S. Now that we know angle S and angle P are the same, because of, look at that right there, they're subtended by the same arc, we're going to end up getting S is equal to, angle S is equal to 23 degrees, because we found that in the question before. Now that we know this is 23, we could find the rest. Well, I'm going to use the sine law because I know the side and its opposite. So sine law. So I know, and we want to find out the angle. So I'm going to keep sine on top. So I'll say sine 23 all over 2.5 is equal to, well, which one do we want to know? We want to know SQR. So this is the one we want to know. We know the opposite is 4.7. And this is going to have to be 2.5. Oh, sorry. And this is sine Q. So we're trying to find that angle. Now to solve for this, we just have to isolate for Q. So first we're going to multiply both sides by 4.7. Okay, so we get 4.7 sine 23 of angle 23 is over 2.5 is equal to Q. Is equal to sine of Q, angle Q. Now, in order to solve this, we're going to end up getting Q is equal to, so we have to take the inverse of that. Okay? And we will end up getting, for an angle, once you plug this into your calculator, you get 47 degrees, I believe. And that's it. All right?